Okay, so one kind of aside I want to make here is this business about the Koshi horizon. So there's a Koshi horizon in, uh, where is it? In this Penrose diagram here. It's right up there. And there's also one here. And what is the Koshi horizon? Well, Koshi horizon is, in fact, people would usually more often talk about that one. But if you take a space-like slice, and we also put some kind of boundary condition at the singularity so you don't have anything flying out of that, this space-like slice determines evolution, again, if we don't have stuff coming out of the singularity, all the way up to here. But if you venture into this region up here, you need Koshi data on here to know what you're going to see. You can't predict it from any initial data imposed down here. There's a new region where stuff can come in. Now, if we look at this Penrose diagram here, it's a little cleaner. Here, if you take a Koshi surface like that, you're okay till you get up to here. Yeah, where you, again, the Koshi data doesn't determine what happens once you're in that region. So that's a little bit weird. Everything that happens inside the black hole is weird. People don't really have a nice way of thinking about it. It's not clear if it's physical. My own feeling is that every piece of data that comes out of solving the Einstein equation has some meaning, but we haven't really decoded how to think about what this picture inside. So I think I am giving a picture of a way of thinking about it in terms of critical behavior and everything, what goes on outside the black hole in this kind of scaling to the horizon and so on. But how we organize the inside with these singularities and what all these funny extra regions mean, we understand that they're there from solving the Einstein equation, but why they're there, if they're physical or not, we don't really have a coherent picture of that. But it bothers people that you can't predict what somebody will see once they're subject to stuff coming in from the next universe. And what makes many people feel better, though not me, is that this picture is unstable under small perturbations. So it's a kind of artificial picture. And it's a little bit, the way that it's artificial is kind of like, this picture is not the real picture. That's the real picture that happens in the physical universe. Here the arguments are a little different. Now, one of the funny things is, notice that if you get to here, you can see the entire, in your causal past, is the entire, so if you compute the proper time along this geodesic, you get to this surface in a finite amount of proper time. So you can see the entire infinite history of the universe flash before your eyes in a finite amount of time. That's pretty weird. And moreover, if somebody is sending you Morse code messages, desperately trying to get a response, not knowing you're out of causal contact, they do it forever. They're infinitely persevering, trying to reach you. They will completely fry you because all that energy will, all that, you shine the flashlight at an infinite amount of time and forever, and it be received here in a finite amount of time. So that means that perturbations, waves coming in here, have a tendency to kind of pile up and have an infinite energy in this region. And then there'll be some, of course, the gravitational field will sense that. And generally what people think is that you get some kind of physical curvature singularity, though exactly how that happens and how many times the geometry is differentiable and whether this is space-like or time-like, we keep, there's a lot understood. It turns out to be an incredibly involved subject. And I haven't followed all the details of it, but suffice it to say, it's generally believed that if you, while this is a solution of the Einstein equation, if you perturb it in any way, this stuff disappears, and so maybe shouldn't be taken so seriously. Okay. Any questions about that? All right. Now I'm going to go on. Maybe I'll go back over here and talk about symmetries. So as I said, it often happens that when you go, maybe I'll leave this picture here, that when you get to a critical point, you get extra symmetries. Now, how do we think about symmetries in general relativity? Well, under a diffeomorphism, the metric, under a diffeomorphism zeta, the metric g mu nu infinitesimally transforms according to the Lie derivative, which I'll just write it once here, is zeta alpha d alpha g mu nu plus d mu zeta alpha g alpha nu plus d nu zeta alpha g alpha mu. And through some identity, which I find cool every time I write it out, this is just equal to the symmetrized covariant derivative of the vector field with an index lowered. Okay, so this is the a general diffeomorphism acting on the metric, and of course it's diffeomorphisms. That's the symmetry of general relativity, and if we have one solution of the Einstein equations and we do a diffeomorphism, we get another solution of the Einstein equations, and of course there's a lot of subtleties about whether or not those two things, those two different solutions that differ by something like this, often they are regarded as physically equivalent, but not quite always. I'm not going to go into that detail now, but a particular interest is a vector field which has the property that its Lie action annihilates the metric. That's called a killing vector. And killing vectors infinitesimally, they're diffeomorphisms, they infinitesimally generate an isometry of the metric. And so Killing vectors generate isometry, and it's obvious. An obvious Killing vector is an obvious Killing vector is, let me call it zeta t, is as a vector field. So that's zeta t alpha d alpha, which is just equal to d by dt. So the components of zeta upstairs are 1 if the alpha is t and 0 otherwise. And it's obvious that that satisfies this because in the first term, the metric is independent of t, so the t derivative vanishes. And in the next two terms, there are no the metric doesn't have any components with a t in them except gtt, but then nu has to be t and dt on zeta is 0. Okay, so it's easy to check that's a Killing vector. But then there are 3 more. So that corresponds to the time translation invariance of the metric. But then there are 3 more. We could call them R, which is d by d phi. That generates phi goes to phi plus constant. That's the axisymmetry of the metric. You can check it in exactly the same way. It's obvious from that expression. And then, of course, it's not just one rotation. There's 2 more. And those are generated by S equals cosine phi d theta minus cotangent theta sine phi d phi. And t equals minus sine phi d theta minus cotangent theta cosine phi d phi. And so these correspond to the other 2 rotations, right? So these 3 vector fields are the 3 Killing symmetries of rotational Killing symmetries of the Riesner-Nordstrom metric. And now, of course, those rotations don't commute, and that is reflected in the Lie bracket algebra. They form a group, which is SO3. And if we take, I won't go through this because hopefully you saw, well, anyway, I won't go through this, but I can form linear combinations of them so that zeta I of these 3, which, so that their commutator, by which this is defined as the Lie derivative with respect to zeta I of zeta j. That's the Lie bracket. It's minus the reverse I and j. So it's antisymmetric. That's equal to epsilon ij k zeta delta kl zeta l. So that's the rotation group. And so what we say here is that the Lie bracket algebra of the Killing vector fields is the same thing as the Lie algebra of the symmetry group of the geometry, right? So we have rotational symmetry and just abelian commuting time translational symmetries. Okay, now all these apply to all of the Riester-Nordstrom spacetimes, but the really interesting thing that happens is that in the near horizon region, you get more symmetries. These symmetries become enhanced to a bigger group. Now, this rotational symmetry, this SO3 rotational symmetry, just goes along for the ride. So when we get to the near horizon region, this Robinson-Bertaudy universe, there's still an S2 factor. The rotational group acts on that S2 factor, and you know that you don't even have to be extreme Riester-Nordstrom. That just sort of factors out of everything. That's not the interesting part of it. The interesting part is that this commuting abelian time translation symmetry becomes embedded in a non-abelian group that acts on the ADS2 geometry. So how does that work? Okay, let me define tau plus or minus equals equals tau plus or minus y, where I'm looking at the top equation there that I wrote, whatever, half an hour ago. Then in those coordinates, ds squared over q squared is equal to, I'm just going to pull the q out, is equal to minus d tau plus d tau minus over tau plus minus tau minus squared. And I guess I have a factor of 4 here. Tau plus minus, yeah, I guess I need a factor of 4 here. Let me instead put a 1/2 here. Okay, so then, and then I have plus the sphere factor, which I think I won't write again because it's just going along for the ride. All right, now let's look at time translations, d by dt, which becomes d by d tau, up to an overall factor. So there's nothing here that, there's nothing to fix the normalization of, well, you might fix the normalization of d by dt by demanding it be 1 at infinity. But that's a little bit arbitrary because it's still a killing vector whether it's 1 at infinity or not. Now, what's more natural, so if you're out at infinity, but once you get in this region, you may or may not want to normalize your generators according to something that happens at infinity. In particular, when you're forgetting about the region at infinity, it's not really very relevant for the normalization. On the other hand, for the sphere factor, you know, there's a canonical normalization. You always want d by d phi to be normalized such that you get back to where you started from when you shift by 2 pi. And similarly, another way of saying it is you want to normalize these generators so that they obey this relationship with epsilon ijk equal to plus or minus 1 or 0, not plus or minus 17. So there's a natural normalization for a group action which is compact and supposed to be periodic. Okay. So we'll see how that we're going to get a natural way of normalizing the killing vectors in the near horizon region. So let me call this, well, there's a killing vector which is just d plus d minus. So that is just d by dt. That's time translations in these coordinates. Let me call it zeta minus 1. Then there's another one, zeta naught, which is t plus d plus t minus d minus. So this one we can understand as time translation invariance. And what is this one? Where did this one come from? Well, if we look at this picture of the geometry here, in this limit where the asymptotically flat region has been lost, there's a symmetry which moves you up and down the throat. When you have the asymptotic region in there, the points on the throat are not all the same because you can characterize them by their proper distance from the opening of the throat. But in the limit where that asymptotically flat region is gone, there's a scaling symmetry which just moves you up and down this throat, and that is precisely moves you in along these different lines of constant t plus minus t minus. And so that is the scaling, sort of we can think of it as the throat scaling symmetry. And then we have finally this one, which is t plus squared d plus t minus squared d minus. And this one is the surprise. So this one is time translation invariance. So you might want to call this, dilational symmetry or scaling symmetry. And this is sometimes called the special conformal symmetry. This is sometimes also called, sorry. I changed my notation. I had that in my notes, and then I used it for that other metric. Is that your question, too? Okay, so this is and isn't a surprise. It is a surprise from the point of view of, just geometry. But on the other hand, it's well known in condensed matter systems, you often have, and there are even theorems that under a wide variety of circumstances this has to happen. Once you have this symmetry and this symmetry, you get this extra one for free. Okay, so it's something that is common in condensed matter systems. It's only been in the last few years that people have noticed it's also common in general relativity, and it's exactly the same sort of group theoretical structure that is happening. So in a sense, you were kind of the scaling symmetry is a little bit cheap because you had to get a scaling symmetry if you scale everything as far as you go. If you go into the deeper infrared, you keep going and going and going until it becomes self-similar or you reach some kind of fixed point. You kind of, by construction, have to either reach a point. I mean, it can happen if you take some system and you go to longer and longer wavelengths or lower and lower energies that you get nothing, right? If you have a system with a mass gap, you go to low energies, you get nothing. Well, nothing is related by scale transformation. Nothing, so you have the symmetry. But if you find that you have some limiting behavior, it kind of by construction has to be invariant under the scale transformation. The fact that you get this third generator has, under almost any circumstances, has been proven in a wide variety of contexts in general relativity, coupled to all kinds of matter fields and all kinds of different dimensions. Also been proven in condensed matter physics and quantum field theory that as long as you have a unitary theory or whatever, that once you get the two generators, you have to get the third. And in fact, as we'll learn later, it's even better than that. You, in fact, usually get infinitely many more. You get a whole infinite dimensional conformal group, but that's something we'll get to a little later. Yeah.
So you have this near horizon region, and you also have probably this asymptotically flat region, and we understand from like the super rotations and the whole story going on there. What typically, like in your work with Malcolm and Stephen, you have like this the horizon action of the asymptotic symmetry algebra, and now it seems like we have two different algebras, which are not like, so like I don't know what the expectation is for, like you have some sort of Koshi surface, and then like you have boundary terms that are each in different.
Okay, great question, but beyond the scope of what I can talk about now. Yeah. Yeah.
Do extremal black holes always have vanishing surface gravity?
Well, I'm going to get to that. Yeah, soon.
Because it seems like it's tying back to what you were saying about the superconductors and their temperature.
That's right. That's right. Yeah.
If we look at a non-extremal black hole, do we only have the first symmetry?
No, we don't. We only have the first.
But we also can throw out the asymptotically flat region. Now we have the two.
I would say the way I would describe extremal black holes, it's like a condensed, if you have a condensed matter system at finite temperature and you try to go to wavelengths below the temperature, there's nothing. So the same way, you can't, if it's not an infinite distance to the horizon of a black hole. It's not an infinite distance to the horizon of a non-extremal black hole. And now you can do some kind of interesting scaling where, so that's like saying you scale to the horizon and then whoop, it's gone. There's nothing left. You've dropped past it. That's why you need to to have this scaling symmetry. You need to develop this infinitely long throat, and it's kind of geometrically easy to understand that if if there's a non-extremal, it's only a finite distance. So you could never, have a symmetry that takes you up and down the throat as you can in the extremal case. Yeah.
But can't, sorry, there are geodesics that go from some point in the normals part there to R equals Q in finite proper time, right?
Yeah.
So in what sense is there an infinite distance to the horizon?
Along a spatial section.
Oh, okay.
So if I do that, it's an infinite distance. Okay, now, yeah.
But in the real like charge black, the extremal black hole case, we did have the
Um, well, you can think of it, and this is something that people have tried to do for a long time, and actually there might have been really important progress on it just in the last 2 years. You know, usually we would think of starting with the asymptotically flat thing and then adding, and then, you know, putting a black hole or extreme black hole in the middle of that. But you can think of it another way of, you know, starting from the near region, the scaling solution, the Robinson-Bertauti universe, and what do you kind of add to that in order to reattach the asymptotically flat region. So again, in sort of phrasing it in terms of the study of critical phenomena, that's like perturbing the system by something, by a perturbation which is unimportant in the infrared, but becomes important in the ultraviolet, right? So this is the infrared. That's where we're scaling to, large redshift. And then going out to here is the ultraviolet. So you can describe a statistical system that has a scaling symmetry, and then you can perturb that in some way. The words that they use for that is an irrelevant operator. You can perturb that in some way so that the perturbation is unimportant at low energies, but becomes more and more important and eventually completely controls the whole system at high energies. Many very explicit examples of this in quantum field theory. And so people have recently really made some very impressive progress in understanding this as a kind of a system with the scaling, a critical system with the scaling symmetry that you then perturb in a way that produces the asymptotically flat space-time. And this whole kind of dictionary between general relativity and condensed matter systems and critical phenomena, and, you know, it's sort of endlessly rich. And I hope to, you know, get through at least some pieces of it, but mostly, I think this is going to be a second semester, but mostly the next semester. Yeah.
So, by this logic, there should also be some sort of picture if I add a relevance operator and change the infrared dynamics. Is there something that can be said there? Like instead of adding something to change the UV, I perturb the IR.
Right.
With the conformal fields here. Does that correspond to that throat somehow?
Closing off.
Yeah, closing off or opening out.
Yeah. Well, temperature, adding a temperature is changing the system a little bit. So adding a temperature, you know, if you're looking, you know, a temperature has a length scale associated with it, right? If you go to distances scales far shorter than the temperature, you don't notice anything, right? On the other hand, if you go to distances, you know, correlation, if you look at just the correlation between a quantum system at some distance, right? So if you go to very short distances, those correlations are unaffected by the temperature, but at large distances, the correlations become exponentially suppressed due to the finite temperature. Things which are far apart, you know, if you have two systems which are quantum correlated at finite temperature, it's very hard to keep them correlated at distances large compared to the distance scale of the temperature. So temperature becomes is like a perturbation of a system that becomes very important below some scale. But this kind of dictionary, which I've tried to just describe in vague terms without being too explicit, I'm being explicit about the stuff we're being explicit about, has many different aspects. And one, indeed, the thing you mentioned, just perturbing the system, not by temperature, but by some term which deviates the dynamics, which becomes important in infrared, that has also had explicit realizations in this kind of story, though those are more intricate, and they amount to some kind of end in the end of the throat region, not in this direction, but down in this direction. Yeah, which can also be pretty explicitly described. But of course now I'm officially, I'm just telling you classical aspects of extreme Reisner-Nordstrom black holes, but the way that it mirrors with other branches of physics is so beautiful that I didn't want to get to it later and say, now remember when you saw this before a month ago in the extreme Reisner-Nordstrom. Yeah. Yeah.
Sorry, is it their vector field generator of boost along the radial field? Their radial direction?
Is it what?
Is it the generator of boost along the radial direction?
I think that I would think of this one as boosts along the radial direction. So let's see. So the first two generators so these act just on the ADS2 geometry. And the first generator is time translations. So it just kind of acts like this. And let me draw this by a dotted line because it's not nothing special happens to the geometry there. And the second vector field sort of scales you in and out the throat. So it looks like this. Both the first and the second field, vector field, map the horizon, which is just sort of a, it's not really a real surface in two-dimensional. It's kind of like, the grin of the Cheshire cat. You start out with the full geometry, and then you do this scaling, and there's nothing special about this horizon, but you can still mark where it was before you took the asymptotically flat region away. And then the third one, well, it's not exactly this one, but there's some linear combination of these three, which is not too hard to explicitly write down, but it's simply moving you up and down this. It's just sort of global time translations in this ADS2. That's the one that's the surprise. And that's the one that, in this picture here, moves you up and down this snake going through the repeating sequences of of universes.
Is
Yeah.
the norm of it uniform?
What?
Is the norm of that vector field uniform?
I don't think the norm of the vector field is uniform.
I
No.
was thinking if it's not uniform, then it's maybe like translates to different at different rates.
I don't. Let me say one more thing, which may about the important thing about a couple more important things I want to say about this vector field, and then it may help you. And yeah.
Is there a nice physical interpretation for the conserved quantity associated with this size?
Well, um, yeah. It's we can think of it as, this one, there's a conserved charge conjugate to this, which would be the usual mass as defined at asymptotic infinity in the full space-time solution. And this one, well, it's not exactly this one, but it's some linear combination of these that generates this. We can think of it as measuring the energy with respect to the global time right. So I had the t coordinates, which I guess, where are the t coordinates? These ones. So if I write t plus or minus is equal to t plus or minus sigma, but this t is not the same. Let me call it, I shouldn't have used little t for this. Let me call it big T. An obvious isometry of this, when I write the metric in this form, an obvious isometry is d by dt, which is up to a factor of 2, is d plus d minus in these coordinates. Right? That's completely obvious that that's a symmetry of this metric. That thing just moves us up and down here. Now, we can write that. This is not a new, this plus and minus, maybe I should write it d by dt. This plus and minus are not the same as this plus and minus. These coordinates are not the same as these coordinates, right? They're related by one is the cotangent of the other. Okay, so however, this is not a new killing symmetry. It's some linear, if I do a coordinate transformation on these guys into these coordinates, it's some linear combination of those, which is actually not that complicated, but I'm not going to do it right now. So it's some linear combination of these. And this thing is, this guy is obviously the symmetry conjugate to the energy. So this, we could call this, and this is often called global time, because in the global coordinates for ADS2, it generates global time translations. And so this is the conserved quantity is the energy which is conjugate to the global time. That energy is not the same thing as the energy defined with respect to tau, which is just simply proportional to the energy defined with respect to the original t. And in fact, they're very different things. And in fact, so this time is often called, so the original time goes from minus infinity to infinity along these curves. This is often called Poincare time because it's the time in the Poincare patch, proportional to the asymptotic time, the asymptotic energy. So the Poincare energy, which is the usual energy, tends to be continuous, whereas this global energy tends to be discrete because this ADS2 turns out to be kind of like a box. It depends on the system whose energy you're evaluating, but if you take like a scalar field in ADS2, the energy levels will be discrete. So they're very different things. And the existence of this new kind of energy, this new conserved quantity, I mean, all kinds of, a whole world of interesting things comes out of that. Oh, okay, but there is just a couple things I want to say that follow really directly from this. Now, I haven't said, so I can take the Lie bracket algebra of these three Killing vector fields. And it's obvious that it closes, or I mean, maybe 30 seconds, you could convince yourself that any Lie bracket of these things gives you another one. And there's some linear combination, which again, it's not that hard to spell out, but I won't go through it. There's some linear combination of these such that the Lie bracket algebra is zeta I, zeta j is equal to epsilon ijk, eta kl, where this is minus plus plus zeta l. So it's just like the rotation group. So this is the rotation group, that's SO3. That's generators of Lie algebra of SO3. This generates the Lie algebra of SO2 comma 1, which is, you can also think of it as the Lorentz group in 2 plus 1 dimensions. It's also isomorphic to the Lie algebra of another group called SL2R, which is the group of real 2 by 2 matrices with unit determinant. So that is the isometry group of the near horizon region. And we can, in fact, go beyond. It's easy to go beyond the infinitesimal. These Killing vectors just generate the infinitesimal symmetry, but in fact, we can write the global thing, which is T plus goes to A T plus B over C T plus D. And at the same time, T minus goes to A T minus plus B over C T minus plus D, where AD minus BC, they're real number, AD, B, and C are real numbers obeying this. And so these are the SL2R transformations, and that maps, just like with a SO3 rotation, you can map any group on the sphere to any other group on the sphere. With this rotation, you can map any point in ADS2 to any other point in ADS2. Okay, so I guess I should stop there, and well, we'll have more fun stuff about extreme black holes next week.